Today we're going to be working on the 2013 question number 3 FRQ for the AP Calculus test, and in this particular problem we are given the table of values for the volume of this particular cylinder with height of 4 feet and radius of 12 feet. So we're supposed to answer problem A through B, and for letter A, using the midpoint formula using Reimann Sums with 3 sub-intervals, we're supposed to approximate the total amount of water that was pumped into the pool during the time from 0 to 12 hours, and we need to show our work for this particular answer. So first, let's summarize the given information that is given in this particular problem. So we have this table, and also we know that the pool or the cylinder is or has a radius of 12 feet. We also know that its height is equal to 4 feet. We also know that to begin with at t equals 0, there's already 1,000 cubic feet of water in this particular cylinder. So at t equals 0, there's 1,000 cubic feet of water in the pool, and we're also given the value of P of t, which is the function for the water being pumped into the pool. So let's write it down. P of t would be the water being pumped in, and we also have the function R of t, which is also in cubic feet, and this is the rate of the water that's leaking from the pool. So R of t is leaking in or leaking out. So there's an actual function for R of t, and that is 25 e to the negative 0.05 t. So we're given the function or the formula for the volume as well, which is pi times r squared times h, and we're going to be using this later on in this particular problem. But first, let's answer problem letter A. And for problem letter A, using the midpoint formula with 3 sub-intervals, we're supposed to approximate the value of the total amount of water in this particular pool from 0 through 12. So the midpoint formula is given by using 3 sub-intervals. So our intervals will be from 0 to 4, 4 through 8, and 8 through 12. So that's the 3 rectangular shape that we are visualizing in our head. And since it's the midpoint formula, we'll be using the middle value of each of our rectangle, which is in this case f of 2, f of 6, and f of 10. So for number 1, to find the total area or total value or volume of this particular problem, we'll have from 0 to 4. So we know that to find the midpoint or approximate using the midpoint, we simply need to use the interval or the width of the interval multiplied by your midpoint. So in this case, the width of the interval from 0 to 4 is 4. So we have 4 times the midpoint at f of 2. Add it with from 4 through 8, it's also 4. And we're using the midpoint of between 4 and 8, which is f of 6. Plus from 8 through 12, there's also 4 units, or t is equal, or the interval is at t of 4. So we'll have to multiply this with f of 10, which is the midpoint. And to make it a lot easier, what we can do is we can factor out the 4 since all of them have the same interval. So we have 4 outside, and we'll have to add f of 2, which is 46, and add it to f of 6, which is 57, and f of 10, which is 62. And in this case, if we add this all up, it will equal to 165 multiplied by 4, is equal to 660 cubic feet. And this will be the amount of water being pumped into the pool from 0 to 12 by approximating it using our interval. So for letter B, we need to calculate the total amount of water that leaked out of the pool. So this time, instead of using P of T, which is given by the table, we're going to be using this actual function 25e to the negative 0.05t as our R of t, and we're going to find its total amount of water from 0 through 12, which means we're going to be using our integral function for this particular problem. So for problem letter B, to calculate it, total amount of this particular water being leaked out of the pool from 0 to 12 is simply going to be the integral from 0 through 12 of that function, and we know from our previous problem that the function is R of t, which is 25e to the negative 0.05t. So we have R of t dt. So in this case, we're going to be using our calculator. So the calculator is math 9 for integral from 0 to 12, and let's plug in the function of R of t, which is 25e to the negative 0.05x dx, and our calculator will give us this value, which is going to be So now we're going to be using our calculator. So we'll push math 9 for the integral of the function from 0 to 12. And we're going to just plug in the value of R of t, which is 25 e to the negative 0.05 t, or in this case x dx. And our calculator will generate the amount of water being leaked out, and that is 225.594. So we'll have 225.594, and it's going to be cubic feet, because that is the unit of measurement we're using for this particular problem. Now for letter C, we need to use the results that we had from part A and part B to approximate the volume of the water in the pool at time t equals 12. So we need to calculate the volume of the water in the pool using the information that we had. At t equals 0, there's already 1,000 cubic feet of water to begin with. So the volume of the water inside the pool at this particular time, t equals 0, is already 1,000. And we'll add it to the amount of water being pumped in for t equals 12. So it will be the integral from 0 to 12 of our function pt, and we will add it, or in this case subtract it, because this is the amount of water being leaked out, R of t. So this will be from 0 to 12. We're going to be using R of t because that's the amount of water being leaked out from or being modeled by this particular function. So by using our information a while ago, we know that this is just 1,000. And we know from our previous answer that we approximated the value of this function from 0 to 12. And from our answer, it's 660. So we'll use that. And we just need to approximate the value of this function from 0 to 12. So we have that as well a while ago, which is 225.594. And this is subtraction, not addition, because it's being leaked out. So the volume using our calculator, so we have 1000 plus 660 minus 225.594 is going to give us 1434.406. So that will be the volume of the water in this function at t equals 12. So 1434.406 cubic feet. This one is at t equals 12. Problem letter D, we're going to be finding the rate at which the volume of water in the pool is increasing at t equals 8. So we're going to be using the formula for our volume a while ago, which is 1000 plus the interval or the integral from 0 through t of p of t minus 0, this is dt, 0 through t of r of t dt. And since we're looking for the rate at which the volume of the water is increasing, we need to find the derivative of v, which is v prime equals, this will turn into 0 and this will turn into p of t minus this one is going to be r of t by using the fundamental theorem of calculus. So since we're looking for v prime of 8, we'll have p of 8 minus r of 8. In this case, p of 8 can be found using the table of values over here. So p of 8 is equal to 60 minus r of 8, and we know that r is 25 e to the negative 0.05 multiplied by 8. And using our calculator, 60 minus 25, let's find what the value of that function is. 60 minus 25 e to the negative 0.05 multiplied by 8 is going to give us 43.242. 43.242, and since this is a rate of change, it's going to be cubic feet per hour, since that is the unit of measurement for hour that's given to us. So now that we have v prime, we're not finished yet with our work, because on the second part of the problem, we need to find how fast is the water level in the pool rising at t equals 8. And in this particular case, we'll be using the formula for the volume, which is equal to pi r squared h, and find the rate or how fast the water level in the pool rising at t equals 8. So that means we need to find the value of dh dt, or the derivative of the height in this particular function. So we're going to be using implicit differentiation with respect to t. So we are going to find d dt of v, and since this one is, they're both constants because we know the value of r, which is given to us, the radius is equal to 12 feet. So this one is going to be pi times 12 squared times the derivative of h with respect to t. So this one will give us dv dt equal to pi of 12 squared times dh dt. So in this case, we're looking for t equals 8. So we already have the value of dv dt at 8, which is 43.4. So all we need to do is to plug it all in. So we have 43.242 equal to pi times 12 squared times dh dt. And using algebra, all we need to do is to get rid of pi and 12 squared by dividing both sides by pi and 12 squared, and we can cancel this out. And using our calculator, our dh dt, we have 43.242 divided by pi times 12 squared. And the calculator is giving us 0.096. So this is our DHDD, or 0.096. So in this case, this is going to be the rate of change of the water level rising at t equals 8. And this is how we answer 2013 FRQ in our AP Calculus AB exam.